Welcome back, everybody. Today's gonna be fun because I want to talk about a common fabrication problem right here with these three parts. Let me show you. You guys requested on the Fireball Tool Forum about setting up this funky looking triangle where there's some odd angles and lengths and they're not all the same. So would you make a jig? Would you use an angle finder or protractor? Would you make yourself a template? Would you have the water jet cut out something? Would you draw something out on the table? So I want you guys to be thinking about how you'd solve this problem in your head. How would we get this triangle perfect and how would we set it exactly where it needs to go? So here's the scenario. We have three components that make up a triangle. But if you look at each one of these joints, they are an acute angle, which means they are smaller than 45, which makes it very difficult to cut on my bandsaw. So each of these have to be hand cut, hand scribed, and hand measured. These cuts are probably not going to be correctly made to length or accurate. Other problems is that I have ground the points off for welding, so the overall measurement actually doesn't measure correctly because we've shortened it up for fabrication. These joints are not cut perfect. If I use these miter joints, they don't line up perfectly to get me the correct angle. Here's the other scenario. I want these parts not only positioned to make the triangle that I'm going to show right here in this drawing, I want to position these parts weirdly in this table because I'm going to build off of it. So we have two problems. Set the triangle correctly, get the part orientated correctly. I would like to show you guys how I think would be the easiest way to do this. So let me show you. All right, so we have a request on the Fireball Tool Forum for a funny shape like this. And it's basically how do you fixture up angles? Because these are funky, and how do we do it without an extra tool? So we're gonna use the fixture table to set these pieces up. I don't have a material, but what I've done is I've kind of just used their drawing and we've just made this out of 1x2 tube. And this was just my quick sketch of everything, approximate measurements, get everything to turn out right. Remember, this is just an example. I don't know if this is a real part or not, but we are going to fixture it up anyway. So the first thing I want to do is pull in a table to work off of. Here's a 102/54 table. As you can see, it's just a brick. And then what we're going to do is make an assembly from this table, which means we're going to start adding components. What I'm using here is SolidWorks, but any 2D or 3D CAD, we can do the same thing. I want to bring in our little funky triangle. I'm going to place him just like that. So as you can see right now, this triangle is floating on this assembly. As you can see, we're not touching the table in any way, so I'm just going to start creating some mates. Mates are like kind of like glue, or call it Velcro, or a magnet, and I just touch what surfaces I want, and then I make them coincident with the surface, and SolidWorks is pretty awesome at that. So it's at this point in time where we are now touching the tabletop, and what I want to do is kind of think of an idea where I want this to be welded, or where do I want to start. I always like to build in the corner so that I can get to all the sides and don't have to reach so far in the middle of the table. If we put it there, we'll think about how far we have to reach. So these are all little things you need to think about. So I like to work in the left-hand corner as if I was reading a sentence in a book. To get started, we need to give ourselves 3 points. 3 points make a hard to find angle. So the first point I would like to set with, browse my library, and I'm going to bring in a fence block. Fence block is just a 1x2 brick with some holes in it. In this case, we put holes all the way through for CAD modeling, but this kind of represents the true fixture when we can rotate this block around any way we want. So I'm going to do the same thing as I did before. I'm going to mate it there, making it coincident. What we can see here is looking over the top, we need to start aligning the holes. So I'm going to make this hole and this hole tangent, and I'm going to swing this block around. So as you can see, we're pivoting on that top, and I want the computer to match the holes up for me. So I'm going to mate these, and there you go. Just like that. That block is locked in place. Now, I can always come back and move this if it's not in the right spot. I just know when I start putting my part in here that I kind of want to stay away from the corner. I don't want to put this too tight because I need to get in here and weld or do something. Position these as far out as possible, but I have this floating in here just to give me a general idea where I want to put the blocks. All right, so I'd like to have 2 blocks for every part. That's kind of the rule for fixturing. Click Control and left click on the mouse and drag it off. And that gives me another block. And we're just going to mate the same thing. Now there's a couple other ways we can mate this. We can make this parallel or perpendicular, all that jazz, but I just like to use the holes in the table. And as you can see, SolidWorks just knows what I want, and it just makes that part jump. It's pretty smart. Another thing to talk about, I like the blocks going this direction because it creates a nice square edge to the table. If we were to use the side of the block this way, there's a little bit of movement in the pins just because that's just manufacturing tolerances, and these table holes do get some crud and stuff in there, so we don't like the pins fitting too tight, but because of that, they have a little bit of movement. But if you go this direction and you put your material up to it, they don't seem to move that much. Okay, so this is how I kind of like to set it up. So I'm going to select this side of our little triangle and this surface of our block. I'm going to hit mate. And as you can see, we are touching those two blocks. And as you can see, we're sliding around. So we're not constrained yet. So we need one more block, just like this. So I'm going to pull off another one. I'm going to pivot them around. Now I'm just kind of looking to see where I want. Select that bore, mate him up. Kind of like to pivot these off a little bit so I can actually see that it mated. Jump. Those might be a little close, but I think we'll get away with that. So now to mate this surface, we want to use this corner right here. We want a nice sharp point. You can see SolidWorks just jumped that corner together. Excellent. So now our part is constrained, okay? We can't move it. So now what we need to do is, how do we constrain this other side? We need 2 points on every part. We know by looking at this that another fence block is not going to land on a grid and it's not going to touch. Okay, so what we're going to need to pull in is a flexible block, something that we can shift and move forward. The component that does this is called a tooth block. All of these parts you can download at the Fireball Tool forum, or just draw your own, because whatever software you're using. The Fireball parts are overly defined, which means they might bog your machine down a little bit. So these are really simple to draw in CAD. It's just a rectangle. And we try to keep things really simple. Don't add fillets or anything like that will slow the machine down. Where do we want it to touch? Probably somewhere in here. I'm just going to hit Control, select the side, and I'm still holding Control. I'm going to select the bore, and I'm going to hit Mate, and it's automatically going to do that selection for me. You can see how we're pivoting around. We want these blocks to always stay in the grid. We don't want to match it like this. So why don't we want to match it like this? Remember, this triangle isn't going to be here. We haven't technically created it yet, right? We would, in this orientation, we'd have one bolt that's holding this thing down. And in this scenario, our triangle is defining this part. And that's the wrong way to do it. We want to have the table define where this part is located. We don't know how to rotate this in the right angle yet. We'd have to pull out a special tool. We don't know how far off this is extended. So this is bad practice to turn the block. Sometimes we have to do it, but we want to avoid it at all costs. So I'm going to go back in here to my mate, and I'm going to remove that coincident. So what we want to do is stay in the grid. We know how to put this block in this position because of the 2 pins. We don't need a special tool for that. This is the correct way to do it. No special tools. This block is now constrained from twisting. And what we want to do is use this nice fine point right there of the blocks, and we're going to make it touch. And it's going to jump forward. So now this block can't move. It has obviously moved forward off of the circle, but we don't know how far did it move forward. We will get that number later. But with that same principle, we want to just continue this around the perimeter. So we need 2 more to locate this little guy. This is the way the chassis of the tooth block actually works. It's just a blank. There's no teeth in here for modeling purposes. We can add any riser we want onto this. So I've just pulled off the base, and the bases work just fine for this application. We're going to move them around, and we're going to pivot. Excellent. This is looking pretty good. And so like I said, I don't want to get too close to the edge, but I think we could probably go here. The further away we are, the better, but try not to crowd the corner too much. We are locked into a place with this. If we don't like the position, we are kind of stuck. So we gotta kind of choose wisely at this point. For this example, it will work. Okay, again, we're locked into the grid, and I'm just gonna apply that same technique, mating the corner and the surface, just like that, okay? And then we'll just do the same to this guy. Now, the cool thing about this is that we're able to then save this and make modifications later. We can kind of see how many fixtures we're gonna need, which is really helpful here and here. Oh yeah, this is looking good. Corner, mate. When we look at everything, we can see that our part is located, blocked into the grid. We know how far apart we are from the center of the hole. Well, not technically, but it is located a certain distance from the center of this hole out all the way around. We know how to put the blocks in. This is a pretty simple setup. But what happens if we wanted this weird shape in the middle of the table, random? We got to use the fence blocks here because we had a nice straight edge. But what happens if we don't get that opportunity? Let's create another one of these guys. Now what happens if we rotate him around in a weird way? Pretend that this angle is a chassis cross member that's diagonally going from one end of the frame to the other. We don't get to pick where that diagonal goes because we'd love to have it land on a grid so we can use fence blocks everywhere, but that's just not going to be possible, right? I'm just going to randomly place it. I'm just going to go there. So to fix something in position, I can right click or I can hit anchor. There we go. Fix. Okay, so you see now it's permanently locked into this location. Now we can apply the same technique to this. We're gonna have to use tooth blocks to do this. So let's just pull off a tooth block. We'll quickly go around it. I'm gonna pull this one off and I'm gonna swivel them around just a little bit more. I'll do 2 of these setups and then we'll lock it in place. So we're gonna make this real fast. So you can see any angle anywhere on the table we're gonna be able to make. It does not matter. This is pretty straightforward stuff. For the sake of time, I'm not going to go around this one, but it's the same exact process as we just did here. Land all our parts. So now I got all the parts laid around here. Now the question is, how do I know where to put these goofy things? Well, we're missing one important thing, and this is a hole layout. We need to know what hole and where. So we have made this little template, hole indicators right here. Every hole has an ID number. So what we're gonna do is I'm just gonna plop him down like that, switch to my top view. Now if you look at this is just some text that we've actually extruded, making it a part or a component basically. Now I'm just gonna position this part where the hole is. Now the reason why we do this is because sometimes we're adding tables together, we're combining, we might be running vertical, so this part allows us to put the grid kind of in any orientation we want without bogging the machine down too much. Which means is if we started laying all these grids into the table, SolidWorks just has a hard time computing with it. So this is the best way we've kind of found to do this. And as you can see now, every hole has an ID number, A1, A2, A3, and so on. So now we are ready to make a drawing, something we can actually build off of. We're just gonna pick the top and I'm gonna drag it over into our little sheet here. Now, if you notice, we are tiny, so we wanna make it big. And I like to use a custom scale, and I've done this enough times to know that this is probably going to be like a 1:7 scale. And we want this large so we can see it, and a little bit of space around the perimeter to drag some dimensions off into some clear area. What we're looking for is the hole center. Now the tooth block works something like this. We need to know the center of the hole. I select this little icon. It says view temporary axes. So this gives me the center of every single hole on this entire map. Isn't that cool? And then I'm going to come up here and select this little dot. Now, I want to be dimensioning off of the center of this hole to the center of this hole up here. Well, now, if you were to imagine these two pieces mating, which means this center hole, this would be 2 inches off the front. The front of this block would be extended exactly 2 inches. But we're not. We're extended out an unknown distance, and we need to know that. And this distance right here corresponds with the scale that's on the side of the block, so we know how far out to move it, okay? But SolidWorks is a little tricky sometimes when it comes to grabbing these measurements. So I just like to come through here and just give myself a little center point, as if I was to be laying stuff out. This just ensures that I'm grabbing the right mark when I come through here and grab the measurements. So I just kind of work my way around the path, and if you notice, we're always working off the front hole. This is where the tooling would go. So this would be considered 2 inches extended out, or 0, however you want to go about it. But I just like to go through and grab that. As you can see here, we're really close. The block is shifted back behind this hole. So technically it's from this point here to this point here. That is the true measurement. Always to the first hole that's completely visible. Okay, so now that we have all our layouts, what I'm going to do is I'm going to hide all these centers because it just gets way too confusing. And I'm going to come in here into my Smart Dimension tool, and this is just basically a measuring tape. And I'm just going to click it, and then it says, oh, that block has extended 3/8 of an inch forward
off that center line. Now what we want to make sure to do is go into our SolidWorks and make sure that we are set into fractions, and we are set to round to the nearest fraction. So this is set to 1/16 of an inch. This is how accurate I want. I could change this to 30 seconds. I can change this down to the 64th if I wanted, but it's kind of unnecessary. A 1/16 of an inch is pretty standard fabrication. It's what you can read on a tape measure. It's what our scales are set for on the side of the blocks. So a 1/16 of an inch is what we're going to use. And then we just go through here and just click it all. And I like to pull these measurements off to the side so it's a little bit more legible, because it kind of gets confusing in there. And then I'm just going to click these 2 points and it's going to grab me a number, and I don't have to do these blocks because we already know what hole and what grid, so those don't need any dimensions. And we just work our way around the perimeter. And it says you're over defined, and I know. Just try to put them in places where we can read. 1 1/8. Yep. 1 3/4. And then when we go down on the shop floor, I will kind of show you how this all looks in real life. And that's how we do it. And then I'd print this off and save it as a PDF. And I'll see you guys on the shop floor.
So the new Fireball tables have hole ID numbers now, A1, and so on across the grid. So it's easy to identify what hole you're working with, and the grid lines just help your eye follow and track and line things up. It's a real efficient system. Okay, so all I'm gonna do is I'm just gonna follow the map. Let's see how long it takes me. And like I said, you're just looking at the picture. This is just big hieroglyphics. So you could give this job to somebody inexperienced, because no matter what, we're gonna have to sit here and kind of figure out where the fixtures go anyway. Might as well just do that in CAD. All right, we did it. Got all our pieces fit in here. And as you can see, we just followed the map. We're in the right grid, right row, off the first pin. All the tooth blocks extended out where they need to go. Everything's in the grid, and that's as simple as that. So in early designs of this, we had it to where you could have 16ths and 8ths in the same washer. But we found in testing that it would often get confused because it can flip-flop. And that would be a bad day to accidentally have the part positioned wrong because you have the washer flipped incorrectly. So what we've decided to do is isolate the problem. I know that this is on 1/8 of an inch centers. I cannot get this wrong. I can look at the next one over here that's on 16ths of centers, and I know that it is on 16th. There's no confusion. By making it a little less convenient to switch washers out, believe me, it's gonna save you a lot of money in errors with the system. So it's a trade-off. Let's do a little experiment here. How close is this angle? Let's just actually measure it. Okay. Would you look at that? 79 degrees, right on the money. So that just goes to show that this system works and we can trust it. So as you see, I just pulled this out, and that's the neat thing about it is I just put it right back where it went. So it's not a big deal to have to pull fixtures back out, put them back in their same spot. Okay, let's put our parts in. Let's see how bad I did. Could already tell you I did bad just by looking at this. Yikes, yikesy, yikesies. Bad, 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 no fitting. Okay, so that's how bad I did. They don't fit. That's just, all my parts are all wacko. So all my parts are too long, all my angles are incorrect. So I'm gonna have to go back and fit all my parts back into here. So a good thing I didn't go off of my angles or my cuts. So that was the first setup, but what I like to do is set up in the middle of the table, because we're not gonna use any of the grids. It's randomly placed like I showed you in CAD, and let's see the outcome if it's exactly the same. How nice is that? Like literally no tape measure. It's just like, and we're doing random angles in the middle of nowhere for no reason other than we can. Okay, done. How long did that take? 3-4 minutes? Probably pretty fast. Okay, we have both setups done. That was very fast. Let's see if I still did a bad job. Okay, so just like part 1, put all my pieces in configuration 2, and we're getting the same results. All my parts are a little too long and the angles are incorrect. So what I want to do is go back to setup number 1. Let's get all my parts adjusted, coped, sanded down to length, and then we'll see how they fit back in all these other configurations. It really doesn't take much to get all the parts fitting, and you can see how much I got to remove. Just a Sharpie lines width. The other thing we're dealing with is roll. So if the cut is kind of at an angle or a bias, it's gonna make things wider. Keeping things square is gonna be difficult with stuff like this, but the table's gonna tell us we're wrong. All right, there we go, everything fits. I got a little wiggle room here to kind of adjust things around, get my gaps to where I want it. And now from this point, I can clamp it in position. So let's just switch everything over and around. Look at that. exactly like the other one. Who would have guessed? Look at that. Another nice setup. So hopefully you guys see the benefits to this entire system and the whole ID and be able to map out where you want to put your part and not be constrained by the grid lines or anything like that. Just put it down where you want and build around it and still retain the same accuracy. I can see this being a benefit if you want to mirror your parts over, or if you want to come back at a later date and recreate the same thing you did here today. And I didn't pull out my tape measure or protractor, so I know that the table is more accurate than these things. And I just absolutely love the freedom that I have to be able to come down here and create stuff. And once again, as you can see, I'm human and my parts were made incorrectly, even though they were Sharpie lines off. In my mind, I thought that was good, but as you can see, the table said no go. So I like having something check my work, and it really makes the outcome of the product that much better. And if you have more questions, please leave those at the Fireball Tool forum. So thank you guys for watching, and I'll see you guys on the next one.